In the last class, we have studied about the solenoid and we have seen that the magnetic field inside the solenoid. Okay, so what was solenoid? Solenoid was a device or an instrument that consists of n number of turns, n number of helical turns of a wire which was wrapped around a substance, and the magnetic field produced by that solenoid was very large as compared to the straight current carrying wire. So we have also seen the formula for the magnetic field which was inside the solenoid, and the points which were taken outside the solenoid, the magnetic field there, the value of magnetic field there was 0. Okay, so in today's class we will study about the toroid. What is toroid? What is toroidal solenoid? Basically, you have seen that if this is some material and we wrap a coil, we wrap the wire in a helical manner, so this instrument that we obtained was called solenoid. Okay, so what is toroid? When these two free ends of a solenoid is bent to form a ring-like structure, this ring-like structure is known as what? Toroid. Okay, so in this toroid we will find the value of magnetic field on the 3 points like we did in the solenoid. First is A point, which is outside the toroid. Second is B, which is inside the toroid, and third is point C, which is on the axis of the toroid. Okay, so first we will see the construction of the toroid. So imagine the solenoid is bent. Imagine a 3D figure. Okay, I can't draw the 3D figure on the board, so I'll make you imagine that. Imagine a solenoid bent in the form of ring like this. Okay, so toroid is situated in this plane like this. This is a ring. Okay, wait, I'll show you. Yeah, I got this ring. So consider this is a ring of the toroid. Okay, a circular toroid, a solenoid which is bent in a circular manner to form a toroidal solenoid. And in this ring, here are the if I wrap the wire like this in a circular manner, ऐसे, ठीक है, around its diameter. Okay, so this was our ring, and we wrap the wire around the circumference of the wire like this. Okay, so what you see that the wire is in like this. The wire is wrapped like this. So if we throw a current, so it will go like this. Sorry, the wire was like this. We wrap the wire in this manner along the circumference of the ring. So you see that there are 2 points on the ring. Okay, first is the inside, and the second is first is located at the outer diameter, and second is located in the inner diameter. Okay, so if the current is coming like this, so at the point which is inside the diameter, you see that the current is bending inwards direction. Okay, the current is going inwards direction. So we have denoted all the currents inside at the point inside the diameter of the toroid by cross. Okay, because the current is entering at that point. And if you see the point which is at the outer diameter, you see that the current is, for this point, the current is going in the outward direction. Okay, if the observer is placed here in the if the observer is looking from down, so he will see that is at this point which is at inside the diameter, he will see that the current will enter this point, and at the point which is outside the diameter, he will see that the current is leaving this side. So at the points which are at the outer of the diameter, the current is leaving from that point or going out from that point. So we have denoted the direction of current by dot. Okay, so if you see from there, the wire is the points which are located at the inner diameter, the current is going into that point. Okay, so we have taken that as cross, and all the points that are at the outer diameter, you will see that the current is coming coming outwards. So we have denoted it as dot. Okay, so now we have taken a point A where we have to find the value of magnetic field which is located at the outside of the toroid. Okay, so if you take all these points A, capital, if you take all these points like capital A of the radius small a at anywhere outside the toroid, so by joining all those points at a distance small a from the center of the toroid, you will see that they will form a spherical loop, and this spherical loop is nothing but an ampere loop. Okay, so first we are seeing the magnetic field, the value of B at point A, which is outside the toroid. Okay, so at this point A, we have drawn what? We have drawn an ampere loop. So we will apply what? Ampere circuital law. So what does Ampere circuital law state? That the line integration of B dot dl is equal to mu naught times the summation of current which is inside that ampere loop. Okay, so if you will solve this further, you will get that line integration of B dl cos theta is equal to mu 0 times summation of current. Now see, there is a very interesting point that inside this ampere loop you will see two kinds of current. Okay, you will see 2 points, and at those 2 points you will see two types of current. One, if you see that at the inner diameter of the toroid, the current is going inside, and the same amount of current at the outer diameter is coming outside. So both these currents will what? Cancel out each other, and finally the value of summation of current will become what? 0. So if the value of current is 0, this whole term turns out to be 0, and we see that the magnetic field outside the toroid becomes 0. Understood this one? Okay. So now we will find the magnetic field at point B, which is inside the toroid. Okay. Now you consider this point B situated at r dash radius. Okay. So if you take all those points at r dash distance and join them, you will see that by joining all those points, you will form a spherical loop which is nothing but an ampere loop. So at this point B, we will draw an ampere loop, and we will apply what? Ampere circuital law. So applying an ampere circuital law, line integration of B dot dl is equal to mu naught times summation of current. If we solve this further, we see that line integration of B dl cos theta is equal to mu naught summation of I. Now at this loop of r dash radius, do you see any current inside that loop? Obviously no. Okay, so since no current is flowing inside the loop, then the value of sigma I will become what? 0, and this whole term turns out to be 0. So if this whole term turns out to be 0, then the value of magnetic field inside the solenoid becomes 0. Okay, so we have taken 2 points, point A and point B, where point A was located outside the toroid, and we have seen that the magnetic field at the outside of the toroid is 0, and point B, which was situated inside the toroid, the magnetic field there was also 0. Okay, now we will take the third point C, which is along the circumference. Okay, along the axial circumference of the toroidal solenoid. So we will see the value of magnetic field there. So value of B at point C, which is at the axial circumference of the toroid. Okay, so from the previous 2 points, we will take the point C, which is at a distance r from the center of the solid, and if we take all the collection of those points at the axial circumference at distance small r from the center and join them, we will form what? We will form a spherical loop, which is also a Ampere loop. So since we form an Ampere loop, we will talk about the Ampere circuital law. So by applying Ampere circuital law, that is that is line integration of B dot dl is equal to mu naught times summation of current. Okay, so if we solve this further, we get B dl cos theta is equal to mu naught times current I. Now you see that this loop is what? At distance OC, at a distance R, this loop, we are talking about this loop. I will draw with the solid lines for the better understanding. We are talking about this loop. So inside this loop, you will see only one type of current that is going inside, that is going at the inside of the toroid. So the value of I will be the current which is going inside the toroid by all the turns around the toroid. Okay, so what will be the value of summation of I? Summation of I will become n times of current. If we are having n turns in the solenoid, if we are having n turns in the toroid, we will see the sum of current across all the n turns in of the toroid. So the summation of I will become what? Ni. Okay. Now you see this theta. This theta is what? This theta is the angle between the element Dn and the magnetic field. Now you see that inside this circle, inside this Ampere loop, you have seen that the current is entering inside the solenoid. Entering inside means if you find the direction of magnetic field with the help of right hand thumb rule, you see that the current is entering the solenoid. So entering the toroid. So if you take this toroid in this manner and the turns was in this manner, you see that the current is entering the toroid at the point located at the inner diameter. So if you take the direction of current with the help of thumb, and then the fingers, the curling fingers will give the direction of magnetic field. So what is the direction of magnetic field? The direction of magnetic field is around the circumference of that Ampere loop, and also the element dl is also along the circumference of the Ampere loop. So from this it is clear that theta is what? Theta is 0 degree, because both the magnetic field and the element dl are parallel to each other. So by from here you get the line integration of b dl cos 0 is equal to mu naught ni. Okay, so value of cos 0 is 1, so you will get that b line integration of dl is equal to mu naught n into I. And what is the line integration of dl? Line integration of dl is nothing but the circumference of what? Circumference of this Ampere loop. So line integration of dl is equal to what? 2 pi r. So putting the value of line integration of dl here, b into 2 pi r is equal to mu naught ni. Okay, so from here the value of magnetic field will be mu naught ni upon 2 pi r. Now you see that this capital N and 2 pi r is nothing but the you can write n upon 2 pi r is equal to small n. And what was the small n? From the in the previous class I told you that a small n is the number of turns per unit length. Okay, so here the value of small n will be the number of turn per unit length of this toroidal solenoid. And what is the length of this toroidal solenoid? It is nothing but the circumference of the ampere loop. Okay, so substituting this value here, you will get the value of magnetic field as B is equal to mu naught small n into I. Okay, so the what is the conclusion of this? If you take the points which are located outside the toroid and inside the toroid, so both at those both points the value of magnetic field will be 0. And if you take any point on the axial circumference of the solenoid, you will find that the value of magnetic field is mu naught n times I. Okay, so from here this toroid is the topic of this toroid is over. And if you have given the two diameters of the solenoid, if you have given the two diameters of the toroidal solenoid, or two radius of the toroidal solenoid, one is this inner radius, this is R1, and second is the outer radius R2. So at that, if you have given with two radius, then the magnetic field for two radius, the magnetic field will be B is equal to mu naught n I upon 2 pi. You will take the average of those two radius. Okay, so if you have given the two radius, that is the outer radius and the inner radius of a toroid, then to find the magnetic field at the axial circumference, you will apply this formula. We have talked about the solenoid, we have talked about the toroidal solenoid. Now we will see that the force which is exerted on a moving charge in a magnetic field. So our next topic is, so अपन देख रहे हैं कि what is the force acting on a moving charge in a magnetic field. So if I take the three axes, that is, this is the x-axis, this is the y-axis, this is the x-axis, and this is the z-axis. Okay. If we extend this, this will also called what? This is also called z-axis. Now, if I take the direction of magnetic field along this z-axis, okay, this is the direction of magnetic field, and there is a charge which is moving at an angle theta from the magnetic field. There is a charge moving with velocity v at an angle theta from the magnetic field. Imagine that the magnetic field is going inside this board, okay, inside this board like this. All the magnetic fields are going inside the board like this, and there is so this will be what? This will be the direction of magnetic field, and there is a one charge. If I take this as a charge and it is moving at an angle theta, with the magnetic field. Are you getting? It is moving with the angle theta in this direction. Okay, by making theta, so we will get the two components of this velocity. One will be this component, which will be called what? Which will be called v sine theta, which is the perpendicular component. This is the v perpendicular. How v perpendicular? The magnetic field is in this direction. Okay, magnetic field is in this direction. The particle is moving with velocity v at an angle theta in from the magnetic field, and this component will be the vertical component of that velocity. Okay, so you see that this component is making 90 degree with the magnetic field. Okay, so this component will be the perpendicular component of the velocity. Okay, so this will be the perpendicular component, and the component which is in the direction of magnetic field will be what? V cos theta. So we will take it as V parallel component. Okay. So the force acting on this charged particle moving with velocity v at an angle theta from the magnetic field, this force was directly proportional to the magnitude of the magnetic field. This force was directly proportional to the perpendicular component of the velocity, that is what? V sin theta. And this force was directly proportional to the amount of charge that was moving in that magnetic field. So if you combine all these three terms, you will get what? F is directly proportional to Q V B sin theta. And if you remove this proportionality sign, you will get what? F is equal to K Q V B sin theta, and this K is nothing but a constant. So if this value of constant is 1, you don't have to worry about this constant, okay? So if you take this value of constant as 1 by default, so the force acting on a charge moving at an angle theta in the magnetic field is what? QVB sin theta. Okay, and if you convert this equation into vector form, you will get what? F is equal to Q into Q V cross B. Okay, this is, and the direction is n cap. So this formula is of the vector form. So any charge which is moving at some angle theta in a magnetic field, okay, it will be moving. It will be what? It will be moving. It is moving with the velocity v in a magnetic field. Then that charge will definitely experience a force which will be equal to what? F is equal to QVB sin theta. Okay. So we will take three cases here. Suppose this is the current carrying wire. This is the current carrying wire, capital I. Okay. So around this wire, क्या होगा? Wire के around क्या होगा? There will be some magnetic field. Correct. And suppose if I take a charge Q, this is the charge Q moving with some velocity V. Okay, this is a current carrying wire, and around that wire we will have a magnetic field, and this charge Q, there is a charge Q moving with some velocity V. Okay, so I have told you that if there is a charge moving in the magnetic field, always there will be some force exerted, and due to that force there will be what? This charge will bend either outward or in the inward direction. We will see that where will this force act, and due to that force where will this charge bend. It is not the matter of concern right now. We will see in the separate topic that what will be the direction of force that will act on the charge when it is moving in the magnetic field. I am just showing us example. Okay, so this charge Q will definitely experience a force either in the inward direction or the outward direction, and according to that the charge will bend outwards or inwards. Okay, so if you take, we are taking three cases. So case 1, in case 1, if the charge is at rest. Okay, so if the charge is at rest, what will become 0? Its velocity will become 0. Okay, and if the velocity will become 0, so from the formula F is equal to QVB sin theta, this term becomes 0, so the whole terms becomes 0. Okay, so if the charge is at rest, okay, if I take another charge here Q, which is at which is at rest, then the charges at rest in the magnetic field will not experience any kind of force. Okay, so this point is clear. So case second we take if the charge is moving parallel to the what? Magnetic field. Okay, if the charge is moving parallel to the magnetic field, so parallel के केस में क्या होगा? This was the direction of magnetic field, right? And I am saying that the charge is also moving in the direction of magnetic field like this. Okay, this is the charge Q and this is moving in the direction of magnetic field. So you see that the V is parallel to what? B. V is parallel to B. Then theta will become what? Theta will become 0 degree. So from the formula F is equal to QVB sin theta. The theta is equal to 0 degree. So QVB sin 0. So this whole term will become what? 0. So F force is what? 0. So in the second case, that if the charge is moving parallel to the magnetic field means the charge is moving along the magnetic field in the direction of magnetic field. So in that case, the force on that charge will be what? Will be 0. Okay. So now there is one more case. Take a screenshot. Okay, so there is one more case that if the charge, case 3, if the charge is moving perpendicularly to the magnetic field. Okay, if the charge is moving perpendicular to the magnetic field, then you see that the charge is moving in this direction. Okay, the charge is moving in this is a charge Q and it is moving in this direction V. So you see that the charge is moving along the x-axis and the magnetic field is in the z-axis like this. Okay, like this you take, okay. So this is the z-axis and this is the x-axis. So the both the angle between the velocity and the magnetic field is what? 90. So in this case, if V is perpendicular to B, then theta will become what? Theta will become 90 degree. Okay. So from the formula, F is equal to QVB sin theta, and the value of theta is what here? 90 degree. So F is equal to QVB sin 90, and sin 90 you know is 1. So when the charge is moving perpendicularly in the to the magnetic field, then the value of force there will be what? Maximum, and it is given by what? QVB. Okay, so you have to remember this, that if there is any charged particle which is moving in the perpendicular direction to the magnetic field, then the force acting at that charged particle will be maximum, and that force will be given by QVB. So now we have seen that the force acts when a charge is moving in the magnetic field, and we have seen that in the current carrying wire, okay, in this direction, if the charge is moving, so it will bend away or towards the current carrying wire. So now basically what we are trying to say, that we will now see that how will you find the direction of force that is acting on a charge which is moving in the magnetic field. तो उसके दो तरीके होते हैं. First way is the Fleming's left hand rule. Okay, so Fleming, what does the Fleming left hand rule state? We will see that यहाँ पे there are three axes, xy axis, xy and z axis, okay, and I have taken the magnetic field at y axis. You can take at any point, okay, you can take at any axis, okay. If you wish, you can take the value of magnetic field at x axis, you can take the value of magnetic field at z axis, any axis you want to take. Here I have taken the value of magnetic field at y axis, and some charge is moving along the x axis, okay, which is perpendicular to the what, the value of magnetic field, because we have seen that if the charge is moving in the perpendicular direction to the magnetic field, the force there will be what, maximum, and which was given by what, F is equal to QEB. Okay, so if you stretch the three fingers of your left hand in this direction, मतलब basically क्या करना है आपको, बंदूक तानो, ओके, बंदूक अगर इस तरीके से आप बंदूक तान देते हो अपने सामने वाले पे, सो यहाँ पे फ्लेमिंग लेफ्ट हैंड रूल में this finger will show what, this finger will show the direction of magnetic field. This central finger or the second finger will show the direction of what, the direction of motion of charge, okay, in which direction the charge is moving. And you know that when the charge moves, what it will produce? It will produce current, okay. So this will be what, the direction of current. If this is the direction of magnetic field and this is the direction of current, then force will act in the perpendicular direction which is given by this thumb. So here the direction in which the thumb points will give the direction of force. Okay, so that is what I have written here. From the formula F is equal to Q into V cross B, then the force will act perpendicular to the plane of magnetic field and velocity, means the force will act along the z axis. Okay, so if you see that this is the plane, this is the x axis, this is the y axis, here it is the magnetic field B, here it is the value of current or velocity of charge, means the charge is moving in this direction, magnetic field is in this direction, then the force will be what, perpendicular to this plane. Perpendicular to this plane means this xy rest here in this plane, okay, this xy axis rest where, in this plane, okay. So this will be called what, this will be called the plane of xy, then the force will be what, in this direction. So this marker will show what, the direction of force which is perpendicular to this plane. Understood student? अब वो कैसे आएगा देखिए यहाँ पे, from the vector you have studied that यहाँ पे क्या है, V cross B. So V is taken along the x axis, x cap into y cap, sorry, not x cap, y cap. I have taken the velocity at x axis, so this direction will be what, I cap, and B is in the y axis, so its direction will be what, j cap. So this cross product of I cap and j cap was what, k cap. K cap was nothing but the direction along the z axis. So from this formula we get that the force acting on a charge will be perpendicular to the plane of V and B, and I have shown you that the first finger or the index finger will show the direction of magnetic field, and the middle finger or the central finger or the second finger will show the direction of current or the direction in which the charge is moving. Then this thumb will point towards the direction of what, force acting on that charge. So this was what, this was your Fleming's left hand rule to find the direction of force which is acting in the moving charge in the magnetic field. Now second rule is right hand palm rule. This rule, what this rule states that if these four fingers, these, you are the observer, I am pointing towards you, if this is the four fingers and this is showing the direction of magnetic field and this thumb is showing what, this thumb is showing the direction of what, current or the motion of charge, then the face which is towards your side, this face, opening face which is towards your side, this force will, this palm will show the direction of force which is acting on this charge moving in a magnetic field. And that is what I have written here, that if these four fingers indicate the direction of magnetic field and the thumb indicates the direction of current or motion of charge, then the face which is facing towards you will show what, will show the direction of, the palm's face which is facing towards you will show what, it will show the direction of it will show the direction of force which is acting on the charge in the magnetic field. And there is one more thumb rule. There is one more rule. You have seen the right hand thumb rule. Okay, so this rule is commonly used for solving some complex problem. So it is very easy. We will see that too also. So this is called what? This is used in various competitive exams. Okay, for solving some complex problem. अगर आपको सब कुछ भूल जाए तो सबका एक आपने क्या देखा था, करंट का कंडक्टर में मैग्नेटिक फील्ड निकालने का डायरेक्शन क्या था, ये राइट हैंड थंब रूल से निकालता, तो वही देखना है अपन यहाँ पे राइट हैंड। तो एक ही रूल याद रखना बेटर रहता है, राइट हैंड थंब रूल। Now see what you have to do. If you place the palm in the, देखो फोर्स का फॉर्मूला क्या था, फोर्स का फॉर्मूला was F is equal to Q into V cross B। ठीक है, तो आपको करना क्या है, you have to rest your palm in the direction of velocity or in the direction of current। इस तरीके से आपने रेस्ट कर दिया फॉर्म। अब क्या करोगे, रेस्ट करने के बाद you will curl your finger in the direction of magnetic field। मतलब वेलोसिटी से किधर जाओगे, मैग्नेटिक फील्ड की तरफ। तो मैग्नेटिक फील्ड इस केस में इधर साइड है, आप किधर जाओगे, ऐसे जाओगे। तो ऐसे जाओगे, अगर इसको ऐसे इस डायरेक्शन में कर्ल करोगे फिंगर, तो जो थंब का डायरेक्शन है वो क्या होगा, फोर्स का डायरेक्शन होगा। अंडरस्टूड? ठीक है, अगर आप अपने पाम को वेलोसिटी के डायरेक्शन में रेस्ट करते हो और अपनी फिंगर्स को V से B की तरफ ले जाते हो इस तरीके से, तो यहाँ पे जो ये थंब है, ये थंब क्या करेगा, दैट विल शो द डायरेक्शन ऑफ force which is acting on that moving charge in a magnetic field। Understood? तो इस तरीके से देखो, अगर मैं यहाँ पे डायरेक्शन रिवर्स कर दूं, अगर मैं कहूँ कि आपका जो चार्ज इज मूविंग इन दिस डायरेक्शन, और जो मैग्नेटिक फील्ड है क्या है, दैट इज इन दिस डायरेक्शन। ओके, तो ये रूल कैसे लगाना है, ये रूल लेना है आपको अपना थंब, ठीक है, वेलोसिटी की तरफ थंब पाम को रेस्ट करना है इस तरीके से। ठीक है, इस तरीके से दिख रहा है आपको, इस तरीके से दिख रहा है। और V से किधर की तरफ जाना है, B की तरफ। V से B की तरफ जब आप जाओगे, ऐसे आपने लिया, वेलोसिटी की तरफ पाम रेस्ट किया, V से B की तरफ जा रहे हो, तो ये जो थंब है ये क्या करेगा, दिस थंब विल शो द डायरेक्शन ऑफ force which is acting on this charge particle placed in a moving in a magnetic field। Okay, so there are 3 rules, and better will be what, if you remember the right hand thumb rule। And now we will see that if there are both the fields present, both the field means if there are electric as well as magnetic field present, then what will be the value of force that will be acting on that charged particle moving with velocity v under the influence of both electric and magnetic field। And this force is also called what, this force is called the Lorentz force। Okay, so from the chapter electrostatics we have seen that if there is a electric field present and you place a charge in that electric field, what it will experience, it will experience either the force of repulsion or the force of attraction, depending upon the nature of electric field and the nature of charge which you are placing in that electric field। Okay, so that force was what, electrostatic force। So here in this diagram you see that the electric field is along the z axis and the magnetic field is going inside the board, so you take it as y axis। Okay, so both these axes are perpendicular, means the electric field and the magnetic field both are perpendicular, and there is a charge q which is moving with velocity v under the influence of both these fields। So force on q due to electric field will be what, F is equal to QE, this is the electrostatic force, this is due to Fe, electrostatic force। Okay, similarly since the charge is moving, the magnetic field will also apply the force which is called the magnetic force। Okay, so force on Q due to magnetic field, and what the value of force was, FB is equal to Q V cross Q into V cross B. This is what? This is the magnetic force. So net force will be what? The net force will be the sum of the electrostatic and the magnetic force. So the net force acting on the charge Q will be F net is equal to sum of electrostatic force plus sum of magnetic force. So from here you get QE plus QV cross B. So this is this, if you take Q common, then this will be E plus V cross B. Okay. So this net force, this amount of net force will act on the charged particle which is moving under the influence of both electric as well as magnetic field, and this net force is called Lorentz force. You have to remember this. This force is called Lorentz force.